There we go. Get this set up. All right, can everyone hear me? Cool. Are there any questions before we get started today? Okay, I'm gonna wait. I do have an answer to the question that was asked. That was asked on Monday about taking classes online. The answer will basically be yes, you can take a single class online if you are not in the US. But I wanted to, the person who asked that question is not currently on the chat. So, but yeah, just to be clear. So if you are not able to get a US visa, or yeah, let's put it that way. If you do not wind up coming to the US, then the on-ground requirement of taking 8 credits is a visa level requirement. So if you are, if you're not able to come to the US, you don't have to take the full credit load. You're more than free to take a simple 4-credit class or something like that. So I'll reiterate that in a second. But are there any questions before we get started today? All right, I will be uploading a different or a slightly revised version of the homework tomorrow night. So it was pointed out over the chat that I used H twice. Sorry, over the discussion board that I used H twice in the first problem. But even more so in the last problem, there's a pretty significant error that I need to fix. So I give you a formula to verify, and it turns out that I hadn't thought hard enough about it, and the formula is actually incorrect. So that'll be fixed in the new assignment, and that should be uploaded. I'll probably upload that just directly after class because that's done. It just is a bit of a rigmarole to get it on Colab. So, okay. So let's get started then. So let's recall where we were. We were talking about solving. So recall we were solving linear second order although actually I will say second, put in just parentheses higher, because the tactics that we wind up using here are completely, they generalize to degree n. So linear higher order ODEs. And we already looked at, so the first case that we were looking at is the homogeneous case. And I'm going to do everything here in terms of basically second order ODEs, but this of course generalizes. So if we have A1 x double prime plus, oh, sorry, I'm actually going the right order. A2 A1 plus A naught equals 0. So this is your standard linear homogeneous constant coefficient, your second order ODEs, sorry, I should say with constant coefficients. So this is your sort of standard example. These guys are real numbers. Then what we saw was that we could rewrite the solution in terms of, we can actually rewrite this as a system of equations. And that means that we know exactly what the solutions are. Are, I should say generically of the form. Of the form x of t equals c1 e to the r1t plus c2e to the r2t. And so then we saw that to figure this out, to find x, find ri, there's a nice little trick. And the trick is to just set x equal to e to the rt. We can do this, right? Because we can set c2 equal to 0 and c equal to 1 or something like that. And then plug this into the equation and solve for r. Star and solve for r. So in this case, the nice thing is that what's the second derivative? Well, okay, e to the x or e to the rt, straightforward. The second derivative is just going to be r squared e to the rt. So we're going to get a2 r squared e to the rt plus a1 r e to the rt plus a0 e to the rt equals 0, since e to the rt is always going to be non-zero. This implies that we just have a quadratic polynomial. This gives r. Great. So if we solve this equation, then we can figure out, and we can see we'll get both of our values. Generically, anyway, we'll get both of our values for r out of this. Okay. Any questions? All right. So quick example. And so everyone should be able to do this. So find the general solution to the following. x double prime minus yx minus 2x equals 0. Take a second to do that. So in particular, what are the r's going to be in this case? Exactly, yeah. So x is going to be C1 e to the 2t plus C2 e to the minus t. And I'll actually just walk through actually doing that the whole way. And I should note that this, so this here is called the characteristic polynomial. Okay, so again, how do we write this? So this is the answer. So the first thing we do is write down the characteristic polynomial. And the characteristic polynomial is really straightforward, right? We just replace, the relationship here is that each time we take a derivative of e to the rt, we bring down one factor of r. We're going to then divide through by e to the rt. So we just replace each order of derivative with a copy of r of that to that power. So characteristic polynomial in this case is going to be r squared minus r minus 2 equals 0, where of course the x is the 0th derivative, so it's r to the 0 is just 1. Maybe even writing the characteristic polynomial for us is not a step anymore. We could write and solve. Then we go back to, middle school math, and what do we get? Plus 1 minus 2, great. So r equals minus 1 over 2. And then we write down the general solution. In this case, the general solution is just going to be of the form 4x equals C1 e to the R1 t plus C2 e to the R2 t, which in this case is going to be C1 e to, as we had before, minus t C2 e to the 2t or vice versa, it doesn't matter. The final step, of course, would be to find the particular solution. Solution given boundary conditions. So just in the interest of finishing that off and showing an example, we have your typical boundary conditions for a higher degree polynomial will actually be in terms of the derivatives. It could also be fixed by having a higher degree polynomial, so by saying, that the point, so x of 0 is one thing, and x of 1 is another thing, and x of 2, etc. But in general, we're going to need sort of, for a degree n polynomial, just by the exact logic before, we can turn that into a system of n linear equations, which means we're going to have some of n exponentials, which means we're going to have n constants to fix. And so we're just going to need n pieces of information, n equalities about the values of the functions at certain points or the derivatives. So in this case, a pretty typical thing would be like x at 0 is equal to 0, and x prime at 0 is equal to 1, as an example. So in this case, we actually have to write down some equations now. So we have our general solution, and let's look at x of 0, which of course is just going to be c1 plus c2, and we assert that that's equal to 0. And x prime of 0 is going to just be the derivatives, so minus c1 plus 2c2, and we assert that's equal to 1. So solving out quickly, the first equation is going to just give us that c1 equals minus c2. The second equation then is going to give us that 3c2 is equal to 1. And finally, we're just going to get that c1 is equal to, differently. So c2 is equal to 1/3, c1 is equal to minus 1/3. Great. And the full particular solution is x is equal to minus 1/3 e to the minus t plus 1/3 e to the 2t. Okay, any questions? So that's like a full computation here. And, in principle, of course, you can do this for as high a degree of as high a degree of differential equation that you want, provided it's got constant coefficients and it's homogeneous and all these caveats. So quickly to just say it again, so since Sai popped in, Sai, so I checked, and indeed, if you are not on ground in the US, you can take as few credits as you want. So the 8 credit requirement is only for, it's only a visa requirement for on ground. So if you are not able to come to Boston in the fall, you're more than free to take a single class. And again, the nice thing about that is basically all classes should be online through NU Flex. So it should be easier to take courses this fall. Okay. Yes, you can take 4 credits. What is word between given and, sorry, it's boundary conditions. Thank you. Yeah, sorry. Look, little like roundly conditions there. Okay, any other questions? If you're unable to unregister a course from the portal, why don't you send me and Rajab an email about that. We will get that figured out. Yeah. Okay. Yeah, send me and Rajab an email about that. We'll get that figured out because there is still a lot of this. I mean, so that is what I've been told officially, and there's a lot of what's going on, which is that we have the official policies in place, but that doesn't necessarily mean that they're reflected on the tax side yet. So, all right. Cool. So this is basically it. And as long as you've got a linear constant coefficient higher order differential equation that where the right hand side is 0, so a homogeneous one, you can solve it using this insofar as you can solve the polynomial. So in general, though, there's a nice thing that certain differential equations have, which is called the superposition property. For linear homogeneous differential equations, and that's the following. So let's say, so again, I'm going to write this down in terms of second order, but it applies to higher order. So if x1 and x2 are solutions to an equation of the form a2 prime plus a1 x prime plus a0 x equals 0, then so is any linear combination. And the reason this is straightforward, a2 c1 x1 plus c2 x2 double prime a1. The reason here is just that basically all of the derivatives are appearing, well, the derivative is linear and everything's appearing linearly. So everything just sort of factors out. Equals 0, so splitting this all up, we're just going to basically get two separate equations. So we get C1 times A2x1 plus double prime, x1 prime, A0x plus C2 times A2 x2 double prime plus A1 x prime plus A0x. Oh, sorry. I can't write that equality. I'm trying to prove that. So but by assumption, these are both solutions. So this equals C1 times 0 plus C2 times 0 is just 0. Great. Okay. So the superposition property is really nice because it means that if we can find any one solution, then certainly C times that, so any constant times that is a solution. And if we can find two different solutions, then any linear combination of them is as well. So we get not just one single solution, but we get the whole massive family of solutions. Now, of course, we already knew the superposition property held in this case, right? Because, well, we just know what the solutions are, right? We know that the solutions are of this form because we can turn this into a system of linear equations. There are differential equations where the superposition property holds, but it's very, very not clear that the superposition property holds. And it definitely, it tends to be more interesting there, but it's still useful to kind of see it because we're going to use a similar property to construct more general families of solutions here in just a second. Okay. Any questions? Okay, so just to write down the general form for complex roots. So for complex roots, this is fairly straightforward. If the characteristic polynomial say a2r squared plus a1r plus r, sorry, plus a0 equals 0 is solved by something like alpha plus I beta. Then the general solution is, and you can go through and you can prove this yourself. I'd say it's a good little exercise, but basically, you can just write down the solution, do the complex analysis. It's going to be e to the alpha t. It's sort of exactly what we would expect, right? Times some constant times cosine beta t plus some constant times sine beta t. Okay. And this is, yeah. Here's just a little exercise. Solve. X double prime plus X equals 0. There you go. Okay, any questions? Okay, so there is one case that is going to be worth mentioning that I just want to, so I haven't actually said very much about this. So what happens if we actually have equal roots? Yeah, that's good. That's basically, yeah, that's exactly what it's going to be. I just read it off the form here. Correct. Because in this case, alpha is going to be 0. Although it is going to be cosine of t, but yeah. Yeah, so there's a case of equal roots, and so I haven't mentioned anything about here, but I do just want to flag this really fast. So far, we've always assumed that there's we've always assumed that there actually is a full eigenspace. So we've always assumed a basis of eigenvectors 2a in x prime equals ax. It turns out that, yes, so that's basically the form that we're going to get. So it turns out that this is, when you relax this assumption, there's quite a lot to be said. And if you take a serious like abstract linear algebra class, you'll actually think a little bit about what we can say about the possible, the possible Jordan canonical forms and whatnot of real matrices A. It turns out, once again, like many problems, this is a very simple problem to solve over the complex numbers and actually quite a tricky one to solve with real numbers. I haven't mentioned it because it's basically known. If you run into a case where you actually do wind up with without having a full basis of eigenvectors. So if you have an n by n matrix, but n is that you don't have n eigenvectors, then I would say that is a case you can look up. You should be aware that they exist, but don't worry too much about them. That said, the case of double roots in these kinds of higher order polynomials is such a case. So that leads directly to a matrix that does not have a full basis of eigenvectors. So just to flag what happens there, it's exactly what Sai says. If you wind up with equal roots, then what we write down instead, basis of eigenvectors. So assume that the characteristic polynomial has, say, a double root. Characteristic polynomial A2R squared plus A1R plus A0 equals 0. Has double root R equals A, for instance. Or let's say R equals R non. Then the general solution is the following. X equals C0 plus C1 times T, EV or not T. So I'm just going to mention that. So it's actually not really going to come up in the computations we do in this class, but in the case of, and I sort of haven't mentioned it because, of course, generically, if you write down some random matrix, it's like a set of measures 0 that doesn't have a full basis of eigenvalues. But it does tend to come up a lot more in this case of the higher order linear homogeneous constant coefficient differential equations. But I did just want to mention that. All right. Any questions? Okay. Slowly learning how to use this software a little bit more. So let me try to fix this. Okay. So here we go. So a quick question, or a quick temperature check. How many people have seen this before? Because this is either this is a very standard thing, or this is a very standard thing in some calculus classes, but it's something that I actually didn't see in my undergraduate calculus courses. So how many people have seen these higher order homogeneous differential equations? sorry, higher order linear homogeneous. Yeah. So at least one. But it doesn't look like, okay, 2 Di definitely has tube. All right. Taupe. I apologize. Again, if I mispronounced your name, please let me know and see the only way I can figure out to get it right. Okay, so about half. So let me there's sort of nothing hard about these. I can do another example, but I think maybe I'll move on to the more interesting case. So I'd say if you have seen these, if you haven't seen these, just kind of go and review this. There's nothing much more than what we said here. It's just factoring polynomials. And the kind of interesting case is what happens in the inhomogeneous case. Linear, blah, 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 constant coefficient. Constant coefficients. Okay, so of course, the case that we actually wanted to solve, we had something on the left-hand side, right? In fact, if you remember, the equation we're trying to solve here is the heat equation. And the heat equation, the left-hand side here was not 0, or this, sorry, I should say the formula for this for a certain computation. And there, the left-hand, so the right-hand side is not 0. And we want to say a little bit of something about that. So, I mean, I'm going to start with an example here, and then I'm going to start with an example, and then I'm going to say kind of what the general solution is. So, example. Let's say that we have, this might be too simple, but let's equals 2. Okay, so this is inhomogeneous. And it's inhomogeneous because we've got a 2 on the right-hand side. So the next, okay, so we've got 2 on the right-hand side. And so we have to figure out how to solve this. And the issue, of course, is that before we basically solved this by using some information that we knew about what the solution could be, and then, well, I mean, basically appealing to the fact that we had some theory behind us, and then knowing that what the solution was supposed to look like. So in this case, it's maybe a little bit harder to get a full general family of solutions like that. So if we had to guess something for the solution, maybe what kind of thing would we guess? For at least 4 of you know the answer here. But feel free to shout it out in the comments. So you're thinking too far ahead. So in the So it will, there will indeed be some exponential terms, but I should say, sorry, what if I just wanted one solution? So is there something that we could think of? If we can't, it's not going to want to be a pure exponential, right? Because if we plug a pure exponential into the left-hand side, there's no way we can get 2 out because we're just going to be taking derivatives. X equals 1 is, well, yeah, is in fact a great guess. And so, I mean, I would say even more generally, since the right-hand side is constant, so right hand side is constant, so, well, let's guess a constant. Guess X equals C. Right, and so you've actually, so what you've done, Size, you've actually, so you've guessed the constant and then actually solved the correct one. And I'm just going to take a second to go through that logic. So if we guess a constant, guess X equals C. So for X equals C, what we're going to have, well, X double prime is equal to X prime is equal to 0. Great, so we're going to get 2 times C equals 2. So C equals 1. And X equals 1 is a solution. Great. In fact, it is not a general solution, right? So it is, you know, we're not getting a whole family of solutions, we're getting a single one. And so I'll say actually, it is a solution, but it's a particular solution. Okay. Yeah, so how do we take a particular solution then and find a general solution? General Exactly. So we're going to notice that we can add the homogeneous solution on the particular solution. So in particular, what this means, so to find a general solution, we noticed that the following is going to hold. So if XP is a particular solution to solution Q star, and let's say that we have a solution XH is the general solution, or actually it doesn't need to be general. XH is a solution to the homogeneous part of the equation. So the homogeneous part here is going to be the equation x double prime plus 3x prime plus 2x equals 0, right? So we have a homogeneous equation. We make it inhomogeneous by changing the right-hand side, in this case. This is where, in general, in our linear differential equation convention, we're going to put all the powers of x on one side and everything else on the other side. So we have a homogeneous part then and an inhomogeneous part. Usually done by part and inhomogeneous part. So if we can find a solution to this guy, then the following must hold, right? So then if we have x equals x times h, sorry, the homogeneous solution plus the particular solution, this is going to be a solution to star. And just to see it, I mean, this is maybe very straightforward, but we can just write it down, right? So the left-hand side is going to be x double prime plus 3x prime plus 2x is going to be equal to xh double prime plus x p double prime plus 3 times xh prime plus xp prime plus 2 xh plus xp. We can separate these exactly as we did for the superposition computation. We're going to get x h, I'm sorry, I'm not writing very clearly today. Plus 3xh prime plus 2xh plus second derivative of the particular solution plus 3 times the derivative of the particular solution plus 2 times the particular solution. But we know what this is, right? This is, oops, there. This is 0 since xh is the solution to this equation, to the homogeneous equation. And this is 2, since the particular solution is the solution to the inhomogeneous equation. And okay, so of course I did it for a single homogeneous solution, but if we have some sort of a whole family of homogeneous solutions, then it still holds just fine. And what this means is that the general solution is going to just be given by exactly as Sai says, the family of homogeneous solutions plus the particulars. So in this case, we just need to factor the characteristic polynomial, which is going to be r squared plus 3r plus 2 is equal to 0. So factoring that, we're going to get r is equal to 1. We're going to get r plus 1, r plus 2. So r is equal to minus 1 and minus 2. Minus t plus c2 e to the minus 2t, then plus the particular solution, which is, oh, it's not 2, it's 1. And this is equal to x homogeneous plus x particular. Okay, so this is now completely non-mysterious except for how we get this particular solution. So as long as we can find, but what this is saying is as long as we can find one solution, we can find the entire family, or we can find an entire family of solutions. there's a little bit more to be said if we want to actually prove that this is every possible solution. But it's not that much harder to prove. Basically, yeah. I mean, the arguments are basically there. You just show that if you, I mean, the only argument is you have to show that any two particular solutions differ by a homogeneous solution, and that's just subtraction. So, okay. So any questions so far? And then I'll do another example and I'll give you an explanation of how you find this particular solution. Okay. So here's the basic idea. Given a differential equation, given a linear constant coefficient, coefficient. Sorry, I should of course be including ordinary differential equation in here. I've been kind of using ordinary differential equation as elliptical, or differential equation as elliptical for ordinary differential equation in this class so far. But there's of course a whole theory of linear constant coefficient PDEs as well, which we'll talk a little bit about. But so given a linear constant coefficient ordinary differential equation, and we'll just use our example, A2 x double prime A1 x prime A0 x is given by some function, oh, sorry, not some function of x, some function of t. Then what we should guess for a particular solution is the following. For xp. So basically the logic here goes as follows. The first order term tells us that we should look for something in the form basically x is equal, so x should take roughly the form of f. So xp is going to be some constant times C0. But maybe I want to save the C0 for the general constants. So just something in the form of f, right? That at the very least is going to make this plausible. Of course, then we're immediately going to take a derivative, right? So when we expand out here, we then take a derivative. And then so we're going to wind up with some derivative of f on the left-hand side. And so we're going to need a derivative of f on the right-hand side to cancel it. So plus some derivative on the right-hand side. Well, now, of course, when we plug this into this equation, we actually, so this actually holds, this way of finding a general solution, or sorry, a particular solution, it doesn't matter how high the order is. This will always be the case. So now that we've added a derivative to the right-hand side, of course, we're going to wind up with a derivative on the left-hand side again, a second derivative, the derivative of this first derivative. So we're going to need something on the right-hand side to cancel it. It is f of t. Thank you very much. That's correct. So plus b2 is f. Double prime of t, and by the same logic, et cetera, as far as we go. So this expansion looks pretty bad, but in general, it winds up, for most of the functions that we like and care about, it winds up being pretty straightforward. So for most common functions, this actually terminates and has a relatively compact form. Okay. So any questions? I'll do a quick example. Okay, so this is an example. This is about as complicated as we're going to get. And so I'm going to go through this example carefully and then leave maybe the rest to exercise. But so let's say that we have y double prime minus 2y prime minus 3y. Well, sorry, I'll go through this full example, then I'll say a couple of things about right-hand sides, is equal to something like 3t squared plus 4t minus 5. Okay. So solving this out, let's think really fast about the particular solution. So secretly, so this here is going to be our f of t. And our particular solution is going to look like f of t plus all of its derivatives, right? Well, okay, so this is going to look like, well, sum of I equals 0 to infinity of bi f to the ith derivative. But okay, so but once we take the what? So we take one derivative, two derivatives, three derivatives. The fourth derivative of this is 0, right? So we actually run out very quickly. And in fact, what is this? This is just some general degree 3 polynomial. Sorry, degree 2 polynomial. Yeah, it's not quite a Taylor series, because a Taylor series, of course, we're divided. So you could write it out as a Taylor series, you know, but for a Taylor series, we're dividing by 1/2n, and these coefficients are very, very carefully prescribed. But it is a kind of yeah, it is a kind of series, a derivative series, right? And a Taylor series is the only example of that we have so far, or probably the only example that you've seen so far. But yeah, so it is kind of like a Taylor series, but it's not. But a Taylor series is a very specific kind of thing. It's very specific coefficients. But in this case, that's a good question. That's good observation. So in this case, we can look at this. We can say, well, what is this? Well, okay, we take a bunch of derivatives. It's just we have a bunch of constants. It's just some degree 2 polynomial. So let's just write it as definitely running out of letters here. D2 t squared plus d1 t plus d0. Great. Of course, we could figure out, we could write this out actually in terms of the derivatives here. But basically, I mean, really, again, given that the BI are arbitrary, you can show without very much work that you can write down any possible degree 2 polynomial. And so we may as well write down a simple one. Okay. So this is going to be our guess for a particular solution. Although, to be clear, it's not really a guess anymore, right? This is a pretty highly educated guess. And I mean, it is a guess in a certain sense, in that there's a slim possibility that it couldn't work out, but the particular solution should take this form, basically by our considerations when we constructed this series here. Any questions? Okay, so now let's solve for it. So this is a little bit tedious and requires an argument that some people may be more or less comfortable with, but it's a very common argument, so I do want to go through it. So in order to solve for this, we have one equation here, and so we're going to need to write down. Oh, well, sorry. This should also certainly be y, since I've switched to y for this problem. So what do we have? So we've got y equals d2 t squared plus d1 t plus d0. So that means that y prime is going to be 2 d2 t plus d1. Y double prime is going to be 2d2. Great. So let's plug in. So plugging these in, what do we get? So we're going to get, this is going to be a bit of a monster, but let's do it. So 2d2 minus 2 times minus 2 times 2d2 t plus d1. So it's going to be minus 4 d2 t minus 2 d1. Then plugging in, we're going to get minus 3 times the minus 3 d2 t squared minus 3 d1 t minus 3 d0 equals 3t squared plus 4t minus 5. Okay, so here's the argument. Now, these to be equal as polynomials, right? So if I tell you that two polynomials are equal for all t, they must be equal order by order. And so I'll see what that means in a second. They must, sorry for all. So there's a couple of ways to prove this. The simplest is just because all of the derivatives have to be equal, right? So since all of the derivatives have to be equal, that tells you that the highest orders must be equal. Well, then if the the nth derivative is equal, it means the highest orders have to be equal. But then if the n minus first derivatives are equal at 0, that'll kill off the highest order and say that the second highest order has to be equal, et cetera, et cetera, et cetera, et cetera, et cetera. So this is it's a very useful fact. And I can say more about that, or if somebody is interested in seeing a proof of it, I can show you a proof maybe after class. But it is just it's a good fact, and it's good for solving these kinds of equations. So what this means here, right, is that the t squared terms have to be equal. The t terms have to be equal. And the constant terms all have to be equal. So we can work recursively. So we have to have minus 3d2 t squared is equal to 3t squared. Second, we're going to have minus 4d d2 minus 3 d1 times t equals 4t. And then finally, we're going to have 2d2 minus 2d1 minus 3d0 equals minus 5. Okay. Any questions? Okay, so we can immediately see that that d is equal to d2 is equal to minus 1. And I'm not going to go through the tedious algebra, so plugging d2 equals minus 1 into the second equation, we're going to get that, well, I mean, you can see it equals minus 1 to the second equation, on both sides. d1 should be equal to 0. So plugging those both into this third equation, we're going to get that d0 equals 1. Great. And we can write down our particular solution, yp is equal to minus t squared plus 1. Okay. So to finish it off, the last thing we need to do, so are there any questions about finding the particular solution in this case? Again, it's a little bit of a tedious computation, but otherwise it's not too hard. You know, it's sort of just algebra. So, which I shouldn't say, I mean, algebra is not necessarily easy, especially multivariable algebra, but okay, so in this case, so we're going to get that for a particular solution. And so our general solution is going to be a particular solution plus a homogeneous solution. So it's going to be minus t squared plus 1. And then our homogeneous solution, again, we can just squint to this and say, what's it going to be? Well, it's going to be, so minus, what are our factors? Minus 3 and 1. So it's going to be plus C1 e to the 3t plus C2 e to the minus t. To the backwards. No, that's correct. Okay. Yes. Okay. So any questions? So solving these kinds of equations is basically, it's a two-step dance. The first step is that we find a particular solution. It doesn't matter which one. Any of them will suffice because the difference between two particular solutions is a homogeneous solution. And then we solve the homogeneous problem for the full family of general solutions. And we can actually see now, I mean, we would have to argue about, you would have to make some arguments about the case where the general solution doesn't lead to a full family of eigenvectors, sorry, full basis of eigenvectors. But otherwise, you know, the way that we've built up the formalism, you can see that this really should give you the full general solution for these equations. Okay. So question. And I'd say, so that for those of you that have seen this before, I want you to hold off for a second and let folks that haven't seen this before think about it. But what should we guess for the particular solution in the following cases? If we have x prime plus 3x equals 4e to the t. Take 30 seconds to think about it. So again, the homogeneous part's the left-hand side, the inhomogeneous part's the right-hand side. What should we guess for the particular solution? Yeah, so if the right-hand side, so in this case, we want to guess, right, so we're going to want to guess, so this is our function f. F. And so we want to guess f plus all of its derivatives. So f, sorry, b0f plus b0f prime plus, oh, let me actually make this even more complicated so we can see it, because it's, let's say 3t. Right? Plus b2f double prime, et cetera, et cetera, et cetera. Okay, but like all of these derivatives are just e to the, it's just e to the 3t, right? So this is, I don't know, so b naught e to the 3t plus 4 b naught plus 4 times 3 b naught e to the 3t plus, okay, so it's just going to be some thing, some constant times e to the 3t. That's what we should guess. Now, of course, so if you look at this, you could worry a bit. You could say, well, wait a second, the scheme that you've given me on the right-hand side, that looks like we're going to keep multiplying things by 3 forever. That looks like it's going to be some sort of exploding series, right? That actually doesn't settle down into something nice. And that's true. And that's kind of why I should say that this is all being done in a sort of formal sense, right? Sorry, I should say this is all being done in a formal sense. There is no guarantee that the series that I wrote down converges, right? And actually, this is heuristic and does not necessarily converge. It's just trying to get us an idea of what the form of the solution should be. In this case, what we see is that, well, if we're actually in luck, this is giving us some information about the derivatives, etc. So this is giving us some information about the derivatives, and basically we can, of course, make this converge by picking these b's to be whatever we want. But basically, the thing that we care about is that the functional term is always going to be exponential, right? So just like it turned, if we take all the derivatives of a polynomial and we add them together, what do we get? Well, we just get another polynomial, right? So if we take all of the derivatives of an exponential and we add them together, what do we get? Well, we just get an exponential. Okay. What about x prime minus 3x equals 3 cosine of 2t? Yeah, 3 cosine of 2t. Okay, what should we guess for our particular solution in this case? Yeah, so what are the derivatives going to look like? Well, the first derivative is going to be minus sine, then cosine, then minus sine, then cosine, then minus sine, then cosine. Okay, great. But they're all the same form. It's just going to be, and you're absolutely correct, we should guess d0 equals cosine of 2t plus d1 is sine of 2t. Right. Any questions about that? Okay, here's a hint. What's a slightly more fun one? What about x prime minus 3x equals 4 over x? All right, and the hint for this one is that yes, you do indeed get an infinite series. What is it? Any guesses before I show the solution? Or at least, I don't know, solution, before I show what you should guess to try to solve it. So what you should guess here is something in the form, well, it's this plus all of its derivatives, right? Okay, so it's just going to be something like b naught over x plus b1 over x squared plus b2 over x3, etc. So it won't be logarithmic. Well, if we could integrate it, then well, okay, I shouldn't say that. So it's possible that the solution that you're going to get, I don't know. I don't think it does wind up being logarithmic. Certainly, the integral of the inhomogeneous part is, and I'm not for sure if with this equation, if you added everything together, if you got something logarithmic, but you might. But yeah, so you get some sort of non-trivial infinite series, and then what you actually have to do then is, plugging this in, you'll just get term by term some relationship between the VIs. But so this is basically it. If somebody hands you a inhomogeneous right-hand side, what you really want to do is just look at, say, well, okay, let's look at all of the derivatives and let's see, and let's guess that, and then try to solve. And it's a little exercise. I mean, see how far. Actually, I don't know with the left-hand side that I wrote down if there's actually a solution here. But see how far you can, as a little exercise would be to see how far you can get with this this third one. Okay. Any questions? All right. So with a little bit of technology under our belt, and possibly a little bit too much, but it's good to be able to handle anything that we could run into. Let's return to the heat equation. Return to the heat thin equation. So what did we have, right? So we found that the second derivative of u with respect to t was equal to beta times u minus us. Let's make sure I have the sign right there. Yes, good, okay. So now we can rewrite that as a homogeneous linear, sorry, an inhomogeneous linear second order equation. So this is u double prime minus beta u is equal to beta times us. We need a particular solution. So what's our particular solution going to be in this case? So remembering that both beta and US are constant, what should the particular solution be? Oh, sorry, I think I've got a sign incorrect here. Oh, no, I don't. Sorry, I've got a sign incorrect here. Yes, I think beta is fixed to be greater than 0 here. We could go back and I can go back and just look at what exactly beta was. Beta is a whole mess of constants. I think that it is. I think that it is greater than 0. What is it? Beta is, yeah, 2 times the height over k times b. I think 2 times the heat constant over k times b plus w. So I think it should always be positive. So given the kind of thing, so yeah, so okay, so even if we don't know what the particular solution is exactly, given the right-hand side, what should we guess for the particular solution? Yeah, so it's going to be constant. And if we plug a constant in to exactly. So do it in 2 steps. It's constant. Oh, sorry. Let me keep my conventions. Is B naught. So that implies that what minus beta B naught is equal to minus beta US. So our particular solution is just US, just the outside temperature. And what about the general solution now? Yeah, so what is the characteristic? Yeah, so what is the characteristic equation going to be? So here you're predicting the roots of the characteristic equation are going to be 1 and 0. So let's write down the characteristic equation really fast. General solution. So homogeneous part. Yeah, so Dong How it's gonna be plus or minus the square root of beta. Let's write it out because there's a lot of constants and stuff floating around. We've got u's doing various things. Yeah, no, it's totally fine. I was wondering if you dropped the beta. Yeah, so that's so yeah, let's just do it out really fast. What are we gonna get? So we're gonna get r squared. Oh, sorry, the homogeneous part is going to be second derivative times 0. R squared minus beta equals 0. So r equals plus or minus the square root of beta. And U equals C1 e to the root of beta t plus C2 e to the minus root of beta t. Cool. And I would say as well, don't ever feel like you need to apologize for your mistakes. You guys have been watching me. You see how many mistakes that I make. So it's all part of, you can't do this without making mistakes. You just have to get good at recognizing when you've made them and incorporating them into and learning from your mistakes. Okay. Any questions? Oh man, they say that as I'm in the middle of making a mistake plus US. Okay, so we kind of know what that looks like in so basically what this is going to tell us is that we sort of have so in the language that we had before, we have a couple of unique phases here. So in particular, if C1 is non-zero, then the solution is unstable, right? And that's a little odd because that would be some sort of situation where we can just heat up infinitely. So I think unstable for finite time. Oh, sorry. Yes. I'm sorry. I apologize. This I made an even bigger mistake. The variable here is not t. The variable here is x. Sorry, that makes a little more sense. I was starting this going, that's a little worrying. Okay, yeah, good. So at equilibrium is the equation. And this last thing, let's just include what is x. Oh, if you remember, so the picture here, probably should have drawn the picture up there, but the picture here is we were looking at this heat fin, right? Where we have heat dispersing off the surface. And we have a heat source and x is parameterizing the length. So no, in this case, because if you remember how we actually got this thing, right? Oh, you're right. Sorry, you're correct. I've written it in terms of t. It should not be. Thank you. Yeah. So right, because the way that we got this thing right was we looked at some small chunk x, and we then we put our conduction equations across the entire thing, integrated it out. Okay, so let's hear now, starting on let's consider boundary conditions. And I'm just going to go through and do this computation really fast, and then we'll take a quick break. So let's assume that we have the following. So at x equals 0, we have some u star. And then let's assume that the heat fin is long enough so that when we're out at the end, it actually has fully cooled. There's other boundary conditions we could assume. L, we have US. By the way, this is kind of a standard notation now, or it's becoming one, that when we might want to think of U as secretly pretending secretly depending on quite a few variables, right? Like we could loosen up the equilibrium condition as we will next week and start talking about what happens if you depends on time as well. Then this just sort of specifies that what we're changing here or fixing here is the variable x. So in this case, what we're going to get then is u of 0 is equal to, great, c1 plus c2 plus u of s equals u star, u of L, which is going to be c1 e to the root beta L plus c2 e to the minus root beta L plus us equals us. So yeah, and I'll keep that in. And I'm not going to do the algebra out because it's relatively straightforward, but what you get is that u equals u star minus us times e to the root beta L. Let me make sure that I get these coefficients correct here. Yes, so over 1 minus e to the minus 2 root beta L. So minus that plus e to the minus root beta L over 1 minus plus us. There's definitely a 2 here. And there's actually a nicer form that you can massage that into in terms of hyperbolic sines and cosines. And let me just state what that is. Just to state what that is. This is us plus u star minus us times hyperbolic sine of minus root beta x plus root beta L, all divided by hyperbolic sine root beta L. So I want to show you this because this kind of equation, these equations in terms of hyperbolic sines, come up quite often in, they seem to come up quite often in the thermodynamics literature. And what you should always think of them when you see them is in terms of exponentials secretly. That's what's going on in the background. They're nice kind of compact ways to write these things down. They tend to hide and pack in quite a bit of information, which is why they're used. But if you do wind up sort of in the world of either thermodynamics, high energy physics, things like that, you will run into these things a lot. And if you don't sort of know that they're actually like, you know, okay, this is the solution to some kind of heat equation thing. That's what you should always sort of think when you squint at them. Because otherwise they just be like, you know, when hyperbolic sine shows up, you sort of go like, oh my God, what is going on now? So, all right, are there any quick questions? Okay, so maybe let's take like a 7-minute break, just because there's more that I want to say today. Reasonably more than I want to say today. And then, yeah, so it is 2:38 my time. And if you guys want to come back at 2:45, so in about 7 minutes, then that would be great. Pull down my poor tablet. What are the requirements for the final first draft? Yeah, so basically the requirements, again, with the first draft is much more for me to look over what you have and to say something to you. So two things, actually, I'll say this again. I was gonna make an announcement about this when I reposted the second assignment, so I'll do it. I have moved the deadlines back for everything. So we're going to do presentations during finals week. And those presentations, I'll make them at a time when you can do them. I talked to several of the students in Beijing over the weekend. And so, for instance, we will have some people do it during class time. Some people will do it at more sort of 9 in the morning. Sort of more like 9 or 10 o'clock at night, Boston time. And if you have a time request, especially those of you who are in different time zones, and especially those of you who work, please let me know. I'm basically more than happy to have you do your presentation whenever. Of course, I would like as many people as can. It's interesting to see what other folks do. But so the requirements. So the first draft is not due next Wednesday. No, but again, the first draft due date. I would highly suggest that you hold yourself to the next Wednesday due date if you can. And the reason for that is that basically the whole point of the first draft is for me to take a look at what you've done and give you some comments. It's worth 1 point, and it's worth 1 point because it's effectively not going to be graded. And I mean, I would very much like you to turn one in. So the more that you have down about what you're planning on doing, the better comments I can give you. So, I mean, if you can turn in, a 4-page paper that's roughly completed with, some, or let's like roughly penciled in of everything that you're going to do, then there's a lot there for me to look at and try to and give you advice on and try to help you build out the paper. If all you have is a couple of equations, I'm more than happy to take a look at that as well and try to help you with that. But I would say the more you can get done by the due date, the better. I think that I have officially moved the due date for the first draft. No, I haven't. Okay. Oh, wait. Not updated. The first draft, yeah, okay, so I hadn't officially moved it back. The first draft due date, I think I'm going to move back to Wednesday. It's Wednesday the 12th. Well, no, because that's not very useful for you. Let's see. I'm going to move it back to the 11th. And because basically the first draft is only as useful as I can actually get you comments back in time for you to do something about them. So I will move back to the 11th. I would highly recommend that you contact me before then, and I'll be reaching out to everybody in some form over the weekend and just checking up and seeing where you guys are. But yeah, which again, I've got office hours on the weekend now, and I may extend those. I may do a similar office hour on Monday. I know that everyone who's in India can't make the office hour that I have, the official office hour. But again, I would say if you want to talk to me, feel free to shoot me an email, and I'm more than happy to schedule office hours with you outside of class, like whenever works for you. So, and that can be a 15-minute thing, that can be a half-hour thing. Okay, I'm gonna grab more coffee and be back in 2 minutes. Yeah, we are definitely a little in the crunch with the project though, and so I think given that, I think I may make this the last official homework assignment. Maybe, or I might just shorten the next one because I would kind of like to give you guys some of the tools in the next one. The next one's on PD flows, and you get to see some interesting stuff with the heat equation. But I do want you guys to be able to focus on doing your final project. That's a much more interesting part of this class. It's amazing. This is so as I think I've said before. This is the first time that I've taught. I've taught in this course in the summer term, and it's amazing how fast time goes. So yeah, I guess that's two. So yeah, so at this point, that gives you 2 solid weeks to work on your final projects, which is probably enough. So maybe the plan, I'll post the final homework assignment and maybe just do it for half credit if somebody wants to take a look at it. Although at this point, I feel like I've been pretty impressed with your guys' homework so far. I either need to make them significantly harder or something else, because usually for the fall semester class, the grades are actually quite a bit lower. So I've been pretty impressed so far. So I may make it for extra credit, or yeah, make it optional. But I think I may fix this as the final official homework assignment, which is a bit of a pity because there's some other stuff that I would like to say. What are you gonna do? I would like, at the end of the day, I would like to give you guys time to actually work on your final projects. So, all right. Are there any questions before we get started again? Okay. So we took a big detour through second order differential equations. And now that we're back, I wanted to give a quick summary of the heat equations that we have so far. So we had the heat temperature equation relating heat and temperature. And so that was for Q, the rate of change of heat. And U, temperature. And, well, C, the specific heat, actually. Yeah, well, let me say it this way. U, temperature, C, specific heat, and M, thermal mass. We had that Q was equal to Cm du dt. So that was our first equation relating heat, the quantity that we care about, with temperature, the sort of measurable property of the system. So we had Newton's law of cooling. Which I'll generally call NLC. So Newton's law of cooling is going to be roughly that for everything is above and H, the Newton cooling coefficient, and S, the surface area of the interface. We have Q1 is roughly plus or minus, actually, so that the cooling between U1, between areas U1 and U2 is going to be given roughly like this. And, oh, sorry. Between, sorry, I should say cooling here, let me be a little bit more precise. Cooling between a solid and a gas. Or I should say, cooling between two different materials. There's a kind of how we use these equations, and then like, well, okay, we're generally using these for cooling between like a wall and a gas, like the top of a heat fin in the air or something. But like, let's be a little careful about that. Okay. And then finally, we also had Fourier's law of heat flux. Heat flux, and that was the equation that given the heat flux at a location. So the heat flux, J of X, at X, K, the thermal conductivity. We had that J of X is minus K du dx. And so far, we've generally been using these to solve these bulk equations. But just to state it, we've talked about a couple of different kinds of heat transfers. We've talked about heat flux and conduction, and then we've talked about conduction and diffusion. There are other kinds of heat transfer. Sorry. So let me say it, write down what I'm saying. So far we've basically been talking about conduction, but there are other types of heat transfer to be aware of. Talking about heat conduction. So heat conduction is when you have objects that are next to each other but are static and heat travels between them. Heat traveling between static objects in contact. In the interest of time, I'm just gonna sort of say what these things are, but I will write down the names. So we also have advection. So you sort of think about all the different ways that heat can get from one place to another. So basically, advection is, well, you could just have, hot water flowing into cold water, right? So, like in a bath or something, where, what the transfer of heat isn't, that there's two static things, the heat slowly like transfers from one to the other. It's you take a bunch of hot water and you move it over here. That's advection. We also have convection. And big one is radiation. So radiation, we'll take a quick look at a radiation model. The radiation, of course, is when you have objects that are not in contact at all, but heat's being transferred by things like photons moving between them. And these all have different formulas relating them. Of course, advection and convection are some of the hardest to model because those require modeling fluid dynamics, which is, a fascinating set of differential equations as well, but it's something that's a little, it's a notoriously hard problem, right? Solving the Navier-Stokes equation is a millennium problem. You'll get $1 million and be famous if you do it. So, it's a difficult, fluid dynamics is to this day a difficult field. So we have other kinds of heating. We have other kinds of heating laws. Laws? And the answer is absolutely. Yes. And if you go into thermal engineering, you start to, you'll get acquainted with all of the various heating laws and various corrections. In this case, I'm just going to give you like a quick example. For example, in our coffee cup case, we sort of make the assumption that the heat of the air is in fact constant. Well, that's only true if there's like a breeze, moving the newly warmed air away from our coffee cup, or any of the air that's directly in contact with it. As soon as it heats up and takes a little bit of heat away, we have to have a breeze or something moving it off. That's of course not going to be true in general. In the coffee cup case, the cup may slightly warm. So in this case, what you'll usually use these modified equations. So something like du dt is minus hs cm times u minus us times 5/4. So this is a typical this static air correction. Okay. And you can go through and you can solve this and you can compare what you get. But mostly this is just to be aware that there are other heating laws that you'll run into. So of course these ones, if you're interested in sort of going into sort of fundamental physics world or something like that, you tend to use the idealized simple laws. But it's always good to remember, especially if any of you wind up going into, one of the big areas of applied mathematics still is working out, it's working with engineers and working with engineering companies and doing their modeling in the background. And if you're interested in that, you should definitely be aware of these other laws. You're going to talk to engineers about things like heat conductivity. Okay. So now let's get towards what the homework is going to be. So some of you may have taken a look at this already. Heat modeling. In a house. So a house for us basically is going to look like a large box model. So we have different quantities of heat. We have them flowing from one place to another, but we want to now decorate them with a little bit more information. So we're going to want to decorate them with information about how the heat is transferring from one place to another. And we're of course going to use convection. So not convection. We're going to use conduction throughout. You could think about, you could, one could use convection. It's a little more complicated. But we also want to be careful about how we're thinking about our boundary conditions. And we're going to see that we can actually derive some sort of interesting properties about heat and thermal resistance. So, okay. Let's look at a kind of a first example. And that's going to be, so assume that we have a house with a roof, and we just want to look at the transfer of heat between the main floor and an attic. Main, attic, our compartment model, we're going to have heat transferring back and forth between the two of them. We also have outside. And heat potentially transfers back and forth between these systems as well. Okay, so we just need to sort of specify how this heat transfer is going to go down. So let's call the temperature on the main floor U1 and the temperature in the attic U2. And then following, we'll call outside US. So then following the prescription that we had on Monday, we should have mass times the heat for U1 is going to be, well, okay, so how do we get the, what was the interface? It's going to be the surface area between, the surface area between the first floor and the second floor divided by R12. I'm going to define R12 in just a second. Times U2 minus U1. Again, we have to be, make sure that our signs are correct here. We just have to make sure. So if the second floor is hotter, then is the derivative positive? Yes, it is. Okay, great. So plus the surface area between the first floor and outside divided by thermal resistance between them is what that's going to wind up being. Times US minus U1. And similarly, for the attic, we're going to get following. S12 over R12. U1 minus U2 now. S20 over R20 times US. Okay, so what are these terms here? So M is, or MI is going to be the mass of the mass of, roughly the mass of the material, the sort of the thermal mass for conductivity in each floor. Thermal So this includes the air, it includes the building materials, it sort of includes everything that's going to hold heat at a constant temperature. Rij is the heat resistance. Between floors or between the floor and the outside. And it's roughly going to be H over C, right? So it's going to be the Newton cooling coefficient divided by the Newton cooling coefficient divided by the specific heat of the materials, or the weighted average specific heat of the materials. Okay, and this basically tracks this equation up here, right? This is our equation for heat transfer between heat transfer And so yeah, this is our equation for heat transfer. And so for conductivity. And of course, we're going to ignore this the static error correction. I just wanted to mention that that's the thing that happens sometimes. And so we just need to then measure the Newton cooling coefficient for the specific interface, the specific heat, and then the respective masses. And in particular, right, so this is this M here is the thermal mass for the temperature in each situation. And so that's why to bring these equations into a sort of symmetrized form, we just bring the thermal mass over to the other side. And then we can write this in this nice symmetrized form. Okay. Are there any questions though? Because, well, in some sense, this is a direct extension of what we've done. It's non-trivial. Okay, so do you believe me that these are the proper equations here, right? So if we have two rooms and we're conducting heat between the two of them, then we should roughly have just this. We should have these nice, what is the direction of the heat in the first equation? Well, so the direction of the heat is going to depend on the, yeah, that's a good question. So the direction of the heat is going to depend on the, which room is hotter, right? So in particular, and this is kind of, it's worth figuring out and making sure this makes sense, right? So let's ignore the outside for the moment, since if we think about this carefully, it should extend to the outside just fine. So if room 2 is warmer than room 1, then this means that room 1 will be heating up and room 2 will be cooling down, right? So the rate of change of temperature in room 1 will be increasing. Sorry, the rate of change of temperature in room 1 will be positive, while the rate of change of temperature in room 2 will be negative. So that makes sense. So as long as room 2 is hotter than room 1 heating up, room 2 cooling down. And similarly, vice versa. So if it's cooler downstairs than upstairs, then we should be transferring heat from downstairs to upstairs. And so room 1 should be cooling down, main floor should be cooling down, whereas the upstairs should be heating up. So if U2 is greater than U1, then the direction of heat flow is like this. So U1. And otherwise, the direction of heat flow should be like this, greater than U2. But luckily, these equations actually account for both cases. And similarly, the direction of heat flow between the main floor and the outside, and the attic and outside, respectively, is going to depend on the difference in those temperatures as well. Yeah. Any other questions? So it's good to think about. It is really good when you're writing these equations down to think about the directions of heat flow, because it's very easy to write down equations with the incorrect sign. So, okay, question. What kind of equations are these? Like, we had to stare at this and say, so it's a system of equations, but what kind of system of equations is it? What kind of model is this? Right? What mathematics should we use to solve this model? What do we think? If I was, for instance, to put this on your homework assignment and tell you to go solve it, what would you do? Well, the big thing here to remember is that everything in this equation except for u1 and u2 is constant. Exactly. Yeah. So there is this like there's this slight linear shift here, but this is almost a just straight linear system of equations. Up to, yeah, that's exactly correct. So up to a linear shift. Sorry, a constant term. Let me say it that way. Term. Is a linear system of equations. And so what we can do actually is if we write, say, V1 equal to, how do we want to do it? Right, V1 equal to U1 minus S, US, which again, US is constant, and write V2 equal to U2 minus US, then we can write this. This is, well, okay, since S US is constant, so then dV is just du, and this is exactly going to be what? V prime, I'll include the M1 here. Okay, so we've got U2 minus U1. Well, but V2 minus V1 is U2 minus U1 because the US is canceled. Great, so S12 over R12 times V2 minus V1 plus S10 R10 times V1. And similarly, we've got M2, V2 equals S12 R12 V1 minus V2 plus S20 R20 V2. And this is exactly, or V equals A, sorry, V prime equals AV for A properly defined. Okay. Any questions? So this means something particularly nice, right? What this means is that we can actually solve these things out. So we have, this is like a quite general thermal model that we've written here, right? Where we, we started with, so we have some outside, we've got some inside rooms, and we're just connecting them. We write this nice system of equations. It turns out that we can write this as a matrix equation. And so actually, we can write quite general systems if we can just figure out how to write down this matrix. We can write and solve, I should say. Very general such modeling problems. Like in particular, there's nothing, so R is based on the materials, and there's actually, if you go into materials, you can just look up data sheets that will tell you what R is. R is thermal resistance. S is going to be based on just some considerations, on basically what is the wall coverage between things like that. So like for instance, and then M is just the mass, again, it's just the mass of the air plus the materials roughly. And so, you can really do things like, if you have some design for a house, a floor plan, rooms A, B, C, to D, and some outside. And you have something like, a heater in room A or in room C. You can do all the thermal conductive modeling and talk about, and I don't know, heater in room C, and outside you've got, some sort of day-night cycle, something like that. You can actually, in a very general sense, write down a model completely for this situation. Another thing you can do, and this is what I was really trying to figure out a straightforward way to do this on the assignment, to do something sort of this complicated. I was really trying to figure out a straightforward way to do this. Is you can also take something like a space and grid it up, and then write down these transfer equations between each of the grid points. And again, these are linear equations. We can do one thing that we can do very, very, very well in computational mathematics is linear algebra. NumPy, between sort of NumPy, C, and GPUs, like we can do things very, very, very well if we need to do linear algebra. MATLAB as well is what it's built. MATLAB is built from the ground up to do linear algebra. And so anytime we can write something in terms of linear equations, we can just solve huge models. So what I really wanted to put on this assignment, something where we actually took a big map and did all the heat transfer equations between them, but it turns out that's either that's a good challenge and make a good modeling project for somebody, but it was harder than I wanted to put on a single homework assignment. Let me put it that way. It's pretty fun. Okay, any questions? So you're going to look at kind of this on the homework assignment, sort of modeling and mapping and solving these kinds of equations. And of course, the picture is where this is all going. And the reason that I want you guys to look at this is because that move from, so we start off with 2 rooms, and then it's easy enough once we see the form of the equations. If I told you to add a 3rd room or 4 or 5 more rooms, you could basically read off the form from these equations, right? It's not too hard. We just need to know what this, how they're connected together. So then one of the ways that we then move to spatial models, one of the ways that we move to partial differential equations is to say, well, let's do exactly what I was talking about with the grid. Let's make a big grid. Let's put transfer equations on each thing and then see how they spin, then use that to simulate spreading out. And by simulate, sometimes it's numerical simulations, and by simulate, sometimes it's also this is how statistical mechanics is done, by doing formal theoretical simulations and then trying to say, well, what happens when we make the grid finer, when we make the grid less fine, and how do we relate these things to the kinds of physics that we're seeing coming out of fundamental physics? It's quite a fun little game. Any questions? Okay, so let's look at another thing we can do with these heat equations, and this is heat loss. So again, we want to start thinking about larger systems, and we want to start thinking about boundary conditions. So here's the setup. Heat loss. I'll specify through a wall. So we've been talking about temperature, right? We've been talking about the static amount of temperature that is say, held inside a wall or something like that. And what we want to do is we want to relate that temperature now to the actual amount of heat that is being lost from a system, right? That's another, one interesting question we could ask is, what is the temperature of each of these rooms at the time? Another interesting question we could ask is, how much heat are we actually losing, right? Just like the river example, or the river state, keeps the same height, the temperature could be at equilibrium, and we could still have a lot of heat flowing out of the system. So let's assume that we have a standard wall. And inside, we have a temperature of UI. And outside, we have a temperature of U0. And we want to temperature separating wall. So then we considered the actual heat flowing through the wall, and the actual heat flowing through the wall, we got a differential equation. So for temperature separating wall, we got the following differential equation. That was d squared u dx squared equals s times minus sk d squared u times, wow. So we have the d squared u equals 0, and this of course turned out to be, so u equals c1 u, sorry, x plus c2. Here we're going to have x equals 0 and x equals L inside and the outside the wall. And so this is our temperature, but we actually want to say something about heat flow. And to do that, we need to fix C1 and C2. So we want to say something about the heat flux. You can tell it's getting late in the lecture. Say something about heat flux, J of x, through the wall. So first things first, the heat flux should actually be constant, right? That was one of our, the heat flux should be, or sorry, the heat flux shouldn't depend on x. In general, of course, it may, but we assume that we're at thermal equilibrium, so any heat entering the wall of the left-hand side has to exit to the right-hand side. But that's okay, right? Because the heat flux is the derivative of the heat, or is related to the derivative of the heat, right? So it's minus K times the derivative of the heat. So in that case, we are going to get something constant at every point in X. So that's what we want. But in order to make this precise, we need to actually specify some boundary conditions, right? Boundary conditions. So in this case, we're going to use the following boundary conditions. U of 0 equals ui. So the boundary conditions, the first boundary condition is that the inside temperature actually is the temperature inside. Okay, fine. And the second boundary condition is going to be that the external wall uses Newton's law of cooling. We could, of course, assume that both the internal and external walls use Newton's laws of cooling. But for now, we're just going to assume one, and we'll see why, because there's a very nice thing that winds up happening. So the Newton's law of cooling condition is that J of L equals sine right H times sine right, write it on a line with enough space. So J of L is equal to H times U of L minus U outside. So we have positive heat flow outside. So again, just thinking about signs, right? We've got positive heat flow outside, provided that at the boundary, the temperature outside is lower than the temperature inside. Good, so the sign checks out. Okay. Any questions? Oh yeah, so I was just thinking a little bit, right? Because should this be plus or minus? I'm kind of stipulating it, but if you remember, J is the flux, and so J is the heat flow in the positive direction, roughly. The heat flow, yeah, J being the flux, and so we would imagine that at the boundary of the wall, since we're assuming U is giving us the temperature inside the wall, it's not giving us the temperature anywhere else, that heat would be flowing. And positively, if the temperature inside the wall is greater than the temperature outside the wall, right? In that case, then we're warm in the outdoors, heat is flowing out, and so this should be positive. So that checks out. Yeah, so or heat could be flowing the other way if the outside temperature was higher. That would just mean that we'd have negative heat flux. We'd have heat flowing into the house, the interface. Any other questions? Okay. All right, so let's use these. And I want to point this out as well. To say, it is a lot more common in the thermodynamics game. Usually in mathematics, our boundary conditions are like really straightforward, right? It's like, or at least what you do in, well, they're either really straightforward or really complicated. But what you do in a math class is the boundary conditions are always like X, so U of 0 is equal to 0 and U prime of 0 is equal to something. It's much more common to have boundary conditions in terms of derivatives, in terms of other locations, in terms of all kinds of stuff in the real world. So just don't be surprised by this kind of thing, and just always think carefully about what your boundary conditions are actually stipulating. All right, so let's solve. So first, U of 0, so this is a simple one, is going to be just C2, not supposed to be U of inside. Okay, so C2 is equal to U of inside. Great. Okay, so now J of X, well, that's minus K times du dx. Minus K times du dx is minus K times C1. So this is, which is good again, because we know that J, since we're at thermal equilibrium, shouldn't depend on X. We should have the same heat flow everywhere through the wall. And this is supposed to be equal to then, okay, so yeah, this is this. And so now we've got J of L, and this is supposed to be equal to K1 H times U of L. Okay, so C1L plus UI minus U0. All right, so straightforward, we can rearrange. And we're going to get that C1 is equal to minus H times UI minus U naught over HL plus K. Hopefully, I mean, I can show the steps of the algebra if there's interest, but hopefully straightforward. And then plugging back in, we have that the temperature is UI minus H over UI minus U0 over HL plus K times X. Great. And we can actually now get the heat flow. So the heat loss is just given by J of X, which is just going to be K times H U naught minus UI, just clearing the minus signs, HL plus K. And it turns out we can write this in, sorry, let me bring this equation down. We can write this actually in kind of a nice form. So this turns out to be equal to did I switch things correctly? Sorry, let me just make sure that I'm, so this is minus sign. Ah, sorry. I forgot that there's a negative, sorry, minus K, not just K. So this then is UI minus U naught times L over K plus 1 over H. Okay, so why is this nice? Why have I written things like this? And the reason is that this here is, so this is 1 over Newton's cooling constant. And this is going to be 1 over the length of the wall times K, where K is the thermal conductivity, right? Let's recall how we got this and where our equation comes from here, right? So K is the thermal conductivity coefficient, and K depends on the material inside the wall, right? So here, this depends on the length of the wall and the material inside it. So length of wall material inside. And this only depends on the interface. The interface between the inside and the outside, sorry, between the edge of the wall and the outside air. Okay, any questions? So what this means is this is a term of thermal resistance. These are terms of thermal resistance. And what we can think about, so we can think about L over K and 1 over H as thermal resistances according to different processes. And just like electrical resistance, what we're seeing is that they're additive. So one question is, so I said, okay, so we put a Newton's law condition on the left-hand side, right? If we're going to take this seriously and really say like, well, okay, so if they actually are additive, then we might think then, I'll call this R wall, right? And this is R Newton's law condition. Then how would we add, it's a question. What would happen if we added a Newton's law condition inside? Or maybe I should say, how would we expect instead of does? Because, you know, here, like, this isn't some sort of mystery. We could just add Newton's law condition inside and just go and prove it, right? But how should we expect? So if when we add a Newton's law condition, what happens is this 1 over H term shows up in the resistance. What do you think should happen if we add another Newton's law condition on the inside? How should J of X change? It should decrease. And how would we, can you give me an exact factor by which it should decrease? Based on the resistance analogy? Yeah, so roughly what should happen is that we should actually add a resistance in. So you should get U of I minus U of 0 is now going to be the resistance due to the wall. So it's going to be UI minus U0 of the resistance due to the wall plus the resistance due to the inside Newton's law condition plus the resistance due to the outside Newton's law condition. And roughly this will be UI minus UO divided by L over K plus 1 over H in plus 1 over H out. Where again, 1 over H, I mean, you almost have to go and measure it. You know, if you take precise temperature measurements and pressure measurements and, you know, and materials measurements, you can look up some tables, but yeah. Okay. Any questions? Okay, so let's look at a final application here. Does double glazing windows work? Okay, so what is the idea behind double glazing a window? So those of you who live in Boston or live in places where it gets cold will have maybe some idea. But the idea is that instead of having a single pane of glass, you have two panes of glass, but then you actually have an interface between them. So double glazing, you have glass and then between the glass you have air. More commonly in Boston, you will have glass, and then over it you'll have something like plastic wrap. So, for those of you who are here in the winter, I would highly recommend you can just go buy plastic wrap kits, and you can actually, well, after this, you'll be able to do the computation yourself and actually see that that it does work a little bit, provided all of our assumptions are correct, but they tend to be within. So. Okay, so what do we have? So we're going to have U1 at the left-hand side, then some temperature A at the right-hand side of the glass, then the air temperature, then some temperature UB, and then U2 outside. Inside. Outside. And the idea is, so we just calculate the heat flow. Heat flow to be J equals U1 minus U2 divided by R, where R is the total resistance. Okay, so again, let's assume that we're at thermal equilibrium. So what that means in particular is that the resistance, if we think about the heat flow through the glass, the heat flow through the air, the heat flow through the glass, they're all have to be the same, right? So heat flow J of x must be constant and the same through each medium. Right? If they're not the same, if we have more heat flow, if the heat flow is higher through the first pane of glass, then that means that the temperature of the air must be increasing, right? Or introducing heat into the system, temperature must be increasing faster than we're sloughing it off, so the temperature must be increasing. As long as we're at thermal equilibrium, all these heat flow has to be. So in particular, we should have that the total heat flow is just the heat flow from through the first pane of glass. So minus UA over whatever the resistance in the glass is. And that needs to be equal to UA minus UB, the heat flow through the air. Call this R air. And that needs to be the same as UB minus U2, which is also just going to be the resistance through the glass. We should have the same thermal resistance, right? Modulo those properties that I talked about before. I should say maybe in parentheses, we're assuming the thermal resistance in the glass is the same. All right, so any questions about the setup so far? Okay, so what we want to do then is think about what this is going to mean for us. So if we have no air gap, then the glass is twice as big. So if we have no air gap, then we would assume that this is U1 minus U2 over 2 times RG, right? We have double the resistance, so resistance is sum. So we have no air gap. The two panes are together, and we're just going to get the total sum of the resistance. Great. This is what we want to check against. So what if we do add the air gap then? So assume that, let's assume just for the sake of this, that the temperatures are all close to each other. Close. So we can define a quantity which is going to be the relative heat flux. And that's basically just going to be, so we have our comparison class heat flux. Let me give this a little term. And so then it's just going to be, so in theory, we are improving our heat flux by what percentage, right? So as we move this thing, J will be, hopefully J will be smaller. And so then we'll get some percent, what this will be is this is the percentage improvement. Percentage improvement or sorry, this is the an improvement. This is the percentage of the percentage of total of no error gap. Oh no, sorry, it is percentage improvement. Right, because if J is almost JS, then the numerator will be very, very small, and so we get some. Yeah. Okay, so finally, we also, if we go and we look at this equation that we derived here, we know what the, we know basically the form that the resistance to the wall is going to be. It's going to be the length of the interface divided by whatever the thermal conductivity is. So now, Rg is going to be length of G divided by the thermal conductivity. And similarly, Ra is going to be the length of A divided by the thermal conductivity. And so at this point, you can go out and measure. You can go out and look at the tables. But roughly, I'm just going to write this down, and this is the computation that you get. So the percentage improvement in heat flux, with a little bit of work, we can massage this guy out to be Ra over 2Rg plus Ra. What it winds up looking like. Basically, you can clearly see that the U1 minus U2 is going to cancel, or U1 minus U2 factor is going to cancel throughout. You do have to use these equations here to justify it, but it's just a little bit of algebra. It's not too bad. We can then rewrite this as, sorry, yeah. We can then rewrite this as, well, plugging everything in here, we're going to get, instead of writing this in 2 steps, I'm just going to say if you plug everything in and you push some things through, here's what you wind up getting. You get Ka times La over Kg over La times Ka over Lg divided by 2 plus Kg over La Ka over Lg. And so what we see at the very least is that everything is given relatively. So is given. So the K's we can go look up. So it turns out for glass and air at standard temperatures, Kg over Ka is about 16. So glass is about 16 times more conductive than air. So the thermal conductivity of glass is about 16 times that of air. So if we set R equals the relative length, we definitely want it that way because we definitely want to be able to say, like, if we have a double the gap, triple the gap, etc., then we get that delta is equal to 16R over 16R plus 2, or R equals R over 1/8. So in particular, let's say that we get what we expect. So when R equals 0, there's no difference, right? R equals 0 implies delta equals 0. Good, fine. When R goes to infinity, we have delta goes to 1, which is what we expect, a 100% improvement. So let's actually look at something practical. So what about when r equals 1? So r equals 1 plugging in, we get that delta of 1 about equal to 0.89. So just by taking two flat pieces of glass and sticking them together, if we just separate them by one width of the length of glass, we get an 89% improvement. So that's pretty good. And if you separate them farther, so by the time r equals 4, you get basically about a 97% improvement. Okay, so here's the question. And I thought about putting this in the homework, but at the end of the day, I decided not to. I don't know, maybe I should have. It's a good one. So how good of a job does putting plastic on your windows do? So what this actually says, okay, so what this actually says that this does do a reasonable job. And if you ever go, as you're, as you're, getting to the point where maybe you're, shopping for a house yourself or something in your life, if you actually go and look at windows, they will be rated by this thermal resistance. But in the meantime, model how this would work for putting plastic wrap on windows. I should say maybe not question, exercise. And kind of the limit here that you want to think about. So this is basically the limit where you have two different L's. So instead of LG, you have L1 and L2, and you just take the limit as one of them goes to 0. Okay, so that is sort of, so that is thermal conductivity and boundary conditions. In particular, kind of what I want you to understand from that is this sort of amazing thing that, in general, in mathematics, we tend to not deal that much, or we tend to not deal that much with boundary conditions, or we deal with boundary conditions in a fairly complicated but spatial way. But it turns out that if you think carefully about boundary conditions, even very, very simple equations, right? Like this is like the simplest differential equation, almost the simplest differential equation we could possibly write down. This function's linear. And we still can say like a lot of interesting things and find quite a bit of complexity depending on how we define the boundary conditions. And this is generally true. Like in a lot of the differential equations game, especially at the either applied or at the higher level, is understanding how the boundary conditions work. We can kind of solve things in the bulk very well. It's what happens for the boundary that gets complicated and often very interesting. Are there any questions before I send you off into the hinterlands of the weekend? All right, we'll have a fabulous morning, afternoon, or evening. And do let me know if you have any questions, either over email or over on the discussion board.
Have a good one.